Happy Tuesday, everybody. In this video, we are going to be looking at the post-lab of our second lab in Unit 3. We were looking at falling objects, and the key idea in this was we are graphically and mathematically modeling the relationship between acceleration and mass. So we were dropping objects, and we were recording their acceleration in our laboratory. So your goal was to create a whole bunch of different masses, remember 7 to 10 different masses, and record their different accelerations. After these graphs were plotted, I walked around and I saw a couple of different situations. Most of them looked something like this, where when I saw people who draw in their best fit line, they said it either looked like that, it either had a downward slope, or you even saw some that were pretty darn horizontal. And from here, then what we noticed is we could create our mathematical model, which we're going to do in a second. Most people got something like acceleration is equal to something like 0.0001 meters per second squared over kilograms times mass plus about what we are going to call 9.8 meters per second squared. And so when I look at this value, now remember acceleration can be positive or negative depending on how the slope was. I look at this mathematical model and I look at my graph, and what I can do is I can start to make final conclusions. The first conclusion that you can make, you look at this number and you realize that's a very, very small number in comparison to our y-intercept, which is 9.8. So you look at that, you're like, that's not going to affect it by much. That's a very, very small slope. That means the slope should probably be 0. And if you think about it, what is a zero slope trying to tell you? Zero slope is trying to tell you that really this thing is not sloping upwards or downwards. As mass increases, you realize that acceleration does not change. So a zero slope means if I extended this graph all the way on over here and I said, what about this mass? Guess what? Our mass is going to stay, or I'm sorry, acceleration is going to stay the same. And for our y-intercept, what this is telling you, well, if we go back into the mathematical model, take this whole chunk, call that 0 now, because 0 times mass is 0, meaning in the y-intercept is actually just acceleration is equal to 9.8 meters per second squared. That is the acceleration for really any object in our laboratory. Remember, preface this by saying this is what we did in the laboratory. So our meaning of our y-intercept is that's telling us the acceleration for any object that is falling. Now we're going to say if this is a positive or negative depending on the situation. We were just recording all positive accelerations. That may change depending on how you set up your axes. So what we are doing is we are getting our final model, which is talking about really this, saying, you know what, our acceleration is 9.8. And this is some things that some people knew. However, now we have a reason why that happened. Your job tonight is to talk about why your laboratory numbers are not exactly what our expected values were. A lot of people will say error, and I get a lot of the answers like, it's human error. Well, we need to get a little bit further away from that and say, I know, like you're going to make mistakes as a human being. However, a lot of those mistakes are based upon your procedure and how the equipment works. So you were dropping these picket fences through these things, and I want you to figure out why some of your numbers were 9.6. How would that happen? Why would you get a number that would be less than what you expected it to be? Why would you get a number that would be more? What do you think happened there? I want you to think about that. I want you to come up with different reasons why from your lab. So, conclusion from all of this is we realized that no matter what my mass was, my acceleration stayed the same. In our laboratory, we know the acceleration is 9.8 meters per second squared. It's for any object. So what does this mean? In short falls, aka air resistance can be ignored, neglected. We can look at a ping pong ball, which has a mass of 0.1 kilograms, and we can look at a bowling ball that's going to have a mass of 7 kilograms. And we can say that they are going to be dropping the same distance, both starting off with a velocity that is 0. And I know now that the acceleration for this ball must be 9.8 meters per second squared. Now my acceleration is going to be downward, so in this case I'm going to put in negative. I also know over here my acceleration will be negative 9.8 meters per second squared. So I know that both of these objects should have the same amount of acceleration, which then I can ask the question, which one hits the ground first? And while we know that their accelerations are the same, we know that their initial velocities are the same, and we know that the delta y that they are falling is the same. And once you get three things, we can then again solve for, well, t, the time it takes for them. And you'll notice if we pick an equation, one of our famous equations that we have, delta y is equal to 1/2 at squared plus v naught t, you will realize if that's the same, that's the same, that's the same, that means t has to be the same. So when you guys come into class tomorrow, we will run this experiment. We will realize that the time it takes for these two, it says should be the same. So this is a huge application. No matter how much you feel like that ping pong ball is going to be pulled down less, we noticed in this lab that the accelerations must be the same. I'm talking accelerations, how the object is going to change its speed. Remember, I'm saying this is in short falls. There's this idea of air resistance that starts to kick in once an object starts moving really fast. And we'll talk about cases where air resistance can be thought of. That's usually a windy day or when you really start getting the air molecules are hitting the object a lot more. But for our instances here, we are going to assume air resistance can be neglected. I will tell you in the problem that as well. So, overall, I want you guys to really walk away with understanding this piece right here, understanding why we can say that our acceleration is 9.8 meters per second squared for any object. We have a great laboratory that allowed us to say that. And then tonight, why were your numbers different? And don't just say human error. Thanks for listening. I'll see you guys all tomorrow.